Thank you. Thank you all for coming back. Recall from last lecture, about an hour and a half ago, that we started defining F-polynomials. And I promised that I would start this lecture as I ended the last one by writing down the formula for an F-polynomial. So let A be a basic finite dimensional K algebra, and from now on K is always the field of complex numbers. If I should forget to write C and I write K instead, you should remember that K is equal to C. So if I have any basic finite dimensional algebra, which I write as a path algebra of some quiver modulo some ideal of relations, and if I take any finite dimensional module M, then you define the F polynomial of M as a polynomial in n variables, where n is the number of vertices of the quiver, the Gabriel quiver of the algebra A. And you define it in the following way. Recall that you consider for M, you consider for every dimension vector E, you consider the Grassmannian of submodules of M with dimension vector E. This is a complex variety, and so you can define its Euler characteristic. You take it, and you take a generating series, well, a generating polynomial in this case, for this. So you take the sum over all possible dimension vector of this integer coefficient times a monomial in y1 up to yn. And this is a polynomial with integer coefficients in y1 up to yn. And this is the F polynomial of M. So let's do some examples of this. I'll first do a stupid example, and then I'll do a less stupid example. The stupid example is computing the F polynomial for the zero module. Yes. What are submodules of the zero module? There's only one, and it's the zero module. So the Grassmannian of dimension vector 0 of the zero module is a point, and all other Grassmannians are empty. And so the F polynomial of the zero module is the constant polynomial 1. This did not depend on the choice of my algebra A. So that's the stupid example. Now a less stupid example, let's take, maybe I'll do this over there. Let's take the path algebra of the Kronecker quiver. And let's look at modules over this. Recall that in the very first lecture, we gave the classification of we saw the classification of all indecomposable modules over the path algebra of the Kronecker quiver. And recall that it started something like this. So in mod KQ, you had a module of dimension vector 1, 0, and then a module of dimension vector 2, 1, and then a module of dimension vector 3, 2, and so on. And then you had some tubes. Maybe I shouldn't do that. I should explicit them, at least one of them. You had modules of this form, and so on. And you had a family here of tubes, a P1 family of such tubes. And then you had some other modules here, which I will not write again at the present time. Yes. So this is a reminder on the classification of indecomposable modules. And I'd like to compute the F-polynomials of these few first modules, just to see how it goes. So let's do this here. What is the F-polynomial of the first module, the projective module at 1? So in order to do this, we need to see what are the non-empty Grassmannian, so we need to look at all possible submodules. But this module, if you view it as a vector space, it has dimension 1, yes? So there aren't so many choices for submodules. They have either dimension 0 or 1. So this only has 2 submodules. The 0 module and itself. Yes. And so the Grassmannian of dimension vector 0, 0 of this module has precisely 1 point, this one. And the Grassmannian of dimension vector 1, 0 also has precisely 1 point. And all other Grassmannians are empty, because there are no other submodules. And so my F-polynomial will have precisely 2 terms. One associated to dimension vector 0, 0, so this is 1. And one associated to dimension vector 1, 0. So y1. And the coefficient is the Euler characteristic of 1 point. And this Euler characteristic is 1. So I should put a 1 here, but I'm not going to write it down. Okay, so let's say the F polynomials. Here I'm going to put 1 plus y1 in the place, maybe more space. There we go. So this corresponds to this. Then let's compute the F polynomial of this guy. It's going to be a bit more complicated. This module has dimension 3, so there should be possibly many more submodules. So let's see. In order to do this, you need to find all possible submodules of this module. Let's go through them dimension vector, one dimension vector at a time. Yes. So what's the Grassmannian for dimension vector 0, 0 in this case? So you're looking for submodules of dimension vector 0, 0. There's always only one, yes, the 0 module. So this is always a point. Good. Now, you could say dually, if you look at the biggest possible dimension vector contained here, so dimension vector 2, 1, there's going to be only one submodule of dimension vector 2, 1. Yes, the module itself. So this is also a point. And next we need to check, well, for all dimension vectors in between. Yes, so what are they? So let's write them down. Dimension vector 1, 0, 2, 0, 1, 1, and 2, 1. 2, 1 is already there. I should also write down 0, 1. There. I thought there was one missing. Okay. Okay? So these vectors, these dimension vectors are the one contained between 0, 0, and 2, 1. Yes? These are the only possible dimension vectors for submodules of this guy. So let's see how many we have. So how many submodules of this module do we have of dimension vector 1, 0? Yes? So what does a submodule like this look like? Well, it looks like this. Yes, it doesn't have much of a choice. There's only one module of dimension vector 1, 0. And we'd like to see if this can be embedded here in such a way that all square commutes. Yes? But all square will always commute as soon as I have anything that is an injection here. So if you see that this embedding here can be an embedding towards any subvector space of this copy of K2, subvector space of dimension 1. So I have as many submodules of this form as I have as many submodules as embeddings, or rather as subspaces of K2 of dimension 1. And what variety parameterizes the subvector spaces of dimension 1 inside a vector space of dimension 2? This is the projective line. Yes, lines in a plane. That's the projective line. So I found this Grassmannian. Next, for dimension vector 2, 0, let's do the same. You're wondering how many submodules of this form. Yes, there's only one module of dimension vector 2, 0. It looks like this. And you're wondering how many ways you can view this as a submodule here. Well, you don't have much of a choice. You have to take all of K2 here and 0 here. So there's only one submodule. Okay, I have two Grassmannians left to compute. Let's do the, I've written it last because I've forgotten about it. Let's do the smallest one first. So dimension vector 0, 1. Yeah? I'm looking for submodules of my module that look like this module. This is the only module of dimension vector 0, 1. So I need an embedding like this, such that all square commutes. Yes? But if I have an embedding like this, so an embedding from k to k, a linear embedding that's just multiplying by some scalar, yes? And I want that the two squares commute. Well, you see that if this is equal to this, since this is 0, then this composition has to be 0. So lambda has to be 0. Yes. So that's not an embedding. So there's no submodule of this form. Yes. No submodules of the form. So this Grassmannian is a point. Sorry, is empty. Empty, empty, no submodule. Sorry, we've computed this one. And now perhaps doing the same thing, there's one Grassmannian missing. I'll leave to you as an exercise to prove that if you have any submodule, if you'd like to have a submodule of dimension vector 1, 1, I'm not telling you which this is, because you have a lot of choices here, yes? You could put 0, 0, or 1 lambda, or 0, 1. Yes? All the modules in the tubes. And show that there doesn't exist an embedding. So you can do this as an exercise. This will imply that this Grassmannian is empty as well. So now we've computed everything. We can write down what the F polynomial is. So there's one term for this Grassmannian, dimension vector 0, 0, so that's 1 times the Euler characteristic of a point. That's 1 as well. Okay? Next, here, dimension vector 2, 1, so that's going to be y1 squared times y2, yes, 2, 1, times the Euler characteristic of a point. So the coefficient in front of it is 1. Next, I have this Grassmannian of dimension vector 1, 0, so this corresponds to the monomial y1, and the coefficient in front is the Euler characteristic of p1. This is equal to 2. I have a 2 appearing here. And finally, there's this Grassmannian of dimension vector 2, 0, so I get y1 square, and the coefficient in front of it is the Euler characteristic of a point, so that's 1. All right? So I have it here. Maybe I reorganized my terms a little bit. Okay? So if you want some practice, try and compute the F polynomial of this module, and I'll give you the answer. It's a longer polynomial, and coefficients 3 appear. So, of course, 1 is always there because it's the monomial corresponding to the 0 submodule. Powers 3 and 2 correspond to dimension vector 3, 2. So this corresponds to the Grassmannian of the biggest submodule. And all the terms in between correspond to the other Grassmannians. If you want a hint, why is there a 3 appearing here? This is because some of the Grassmannians will be isomorphic to P2. And the Euler characteristic of P2 is 3. Yes? So I think that this is a good exercise. If you can compute the F polynomial of this module, then I believe you understand how to compute F polynomials in general. Of course, computing an F polynomial in general is very difficult, because in those cases, the Grassmannians are always quite nice. I mean, they're points, or P1, or P2, or projective spaces, or unions of points, and whatever. In general, it can be a very ugly projective variety. In fact, it's a theorem of Reinecke that any complex projective variety can be realized as a Grassmannian of submodules. So it can be as ugly as you want. But in those cases, we're able to make the computations. All right? Maybe one more example. And it's an almost stupid example, but it's not so stupid in the end. I'll take the simplest quiver you can imagine, which is not empty. What's the simplest quiver you can imagine? You got one vertex and no arrows. Yes. And I'm looking at modules over this quiver, over the path algebra of this quiver. So these are equivalent to representations of the opposite quiver. The opposite quiver is itself, there's no arrows. And this is the same as vector spaces over K. Yes, because what's a representation of this quiver with one vertex? It's the data of a vector space associated to this vertex, add nothing else. So representation of this quiver is just a vector space. Okay, good. And now let's look at the following module. I take the vector space of dimension 2, and I want to compute its F-polynomial. So there's only one variable, y1. I'm going to just write it as y. Yes. So I have to look at all Grassmannians of submodules of this guy. But there's, of course, the Grassmannian of 0 submodules, the Grassmannian of submodules of dimension vector 1, and Grassmannians of submodules of dimension vector 2. Yes? Well, what is a submodule of dimension vector 0 of this? It's just a 0 vector space. So this is the usual Grassmannian gr 0, 2. This is gr 1, 2. This is gr 2, 2. Yes. This is a point. This by definition is P1, and this is a point as well. And so you get that this is 1 plus 2 times y plus y squared. And this, of course, is 1 plus y to the square. And 1 plus y is another F polynomial. It's the F polynomial of the vector space of dimension 1. Yes? And in fact, this phenomenon is extremely general. I'll write this as a theorem. So let A be any finite dimensional algebra, basic finite dimensional algebra. And let M and N be 2 A modules. Then the F polynomial of their direct sum is the product of their F polynomials. And as I said, this is extremely general. So if you know how to compute the F polynomials of all indecomposable modules, then in a certain sense you're able to compute F polynomials of all modules. What you would need to do is take any module, decompose it into a direct sum of indecomposable modules, and compute the F polynomials for all of them. Okay. Now, we want to categorify cluster variables. And as I said, in Laurent's talk, you saw a formula, the Caldero-Chapoton formula, which is very similar, but which really did give you cluster variables. This will never give you cluster variables, because the F polynomial is an actual polynomial in y1 up to yn. Cluster variables are Laurent polynomials. Some negative powers appear. So what we'll do now is modify this definition in order to get another formula which will categorify cluster variables. The next section is cluster characters. So now I'll restrict myself. In the last section, all I did worked for any finite dimensional algebra. But in this section, I'll restrict myself to path algebras of acyclic quivers. I want to have a cluster category in the picture. So let Q be a finite acyclic quiver Let CQ be its cluster category. And as we did this morning, I'll take a cluster tilting object, which I'll call T. Basic here means that if I take two different indices, then the direct factors here are non-isomorphic. It ensures that the endomorphism algebra of T is a basic algebra, so I can give it by a quiver with relations. If I could, I mean, in the definition of a cluster tilting object, it's just a homological definition. It's just a vanishing of some home spaces. So I could add several copies of each of the TIs, and it would satisfy the definition. But when I took the endomorphism ring, I would get an algebra that is not given by a quiver with relations, and I don't want that. Okay, so let's define now cluster character associated to T. This is the map taking, this map I'll denote by CC. It takes objects of the cluster category and spits out Laurent polynomials in n variables. And in order to define it, I do this as follows. I need a piece of notation before I can define this. I just said that since I assume that T is basic, then its endomorphism algebra is given by a quiver that I'll call Qt modulo some relations. So this Qt has n vertices and a certain number of arrows. It turns out that this algebra is actually the Jacobian algebra of some quiver with potential. So I will not be using this. I will only be using, for the moment, this quiver Qt. And so if I have an object x in my cluster category, what is CC of x? It is the F polynomial, and I've forgotten to add another piece of notation. So recall that we have a functor home T shift blank, suspension blank, that goes from the cluster category to the module category over the endomorphism algebra of T. Yes? We saw this morning that this functor induced an equivalence between the quotient of the cluster category by the ideal of all morphisms factoring through T, well, at T, and this module category. Yes. So I have this functor, and I really do need it. I have a conflict of notations. Well, what can you do? So I will take my object x here. I will send it. So let's try again, shall we? The first thing I do is I look at the module fx. This is a module over the endomorphism algebra of T. Yes. Then I will take the F polynomial of this module. I apologize for this conflict of notation. But this f is a functor and this f is for F polynomial. I will evaluate this F polynomial in a certain set of Laurent monomials, which I will call y1 hat up to yn hat. And I can give you what yi hat is right away. It's a Laurent monomial. So for j going from 1 to n, you take xj to a certain power, and this certain power is the number of arrows from j to I in Qt minus the number of arrows from I to j in Qt. So that's the number of arrows from j to I in Qt minus the number of arrows from I to j in Qt. This thing here, if you were to define the matrix, the skew-symmetric matrix associated to Q, so if Bt is the skew-symmetric matrix associated to Q, so that's its, the entry ij is the number of arrows from I to j minus the number of arrows from j to I. That's precisely this. Then this thing here is equal to minus bt times what am I doing? No, that's, sorry. Then this number is minus bij. There we go. So for those of you who prefer to think in terms of matrices instead of quivers, this is the definition. And so this is an F-polynomial that I evaluate in some Laurent monomial. So this lives in Z x1 plus minus 1 up to xn plus minus 1. And I need to multiply by a certain monomial taking into account the index of my object x. So what does this mean? So if the index of x is given by, in the basis of the ti's, is given by gi times ti, the sum of these things, then x to this power is equal to x1 to the power g1 times x2 to the power g2 and blah, 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 xn to the power gn. It's the same notation as we've seen before. So that's a definition. Okay? It's like an F-polynomial, but we've tweaked it a little bit. The summation is hidden in the definition of the F-polynomial, which is not on the board anymore. But recall that maybe we can expand this. So Cc of x, if I expand the definition of the F-polynomial, I would get that this is this term, taking into account the index of x times an F-polynomial. And the F-polynomial is the sum over all dimension vectors of the Euler characteristic of the Grassmannian of submodules of f of x times y hat to the power ei, to the power e, sorry. So this is the expansion. And again, if you prefer writing things in terms of matrices, then you can replace this y hat to the power e by, let me change this, by x to the power minus bt times e. You can check that this is equivalent. This is just a different way of writing the yi hats. Let me not erase the example. So one thing we can notice right away, without doing anything more, is that, I'll write this as a proposition, if you apply the cluster character to a direct sum, then you get the product of cluster characters. And why is this true? It's by using what we know about indices of direct sums and F-polynomials of direct sums, yes? So this thing here, by definition, is x to the power the index of x plus y times the F-polynomial of the direct sum of f of x and y applied to y hat. But we know that the index of a direct sum is the sum of the indices so you can split this into two. And we know that the F polynomial of a direct sum is the product of the F polynomials. So the real proof was the multiplicity of the F polynomials. I haven't done it, yes. But I believe that Laurent will be doing something, or has already done something of this form. You will prove it, okay. Laurent will sorry for putting pressure on. But, okay. So Laurent will prove this multiplicity of F polynomials in a slightly different version. And this, of course, if you reorganize this with this, and this with this, you get that this is cc of x times cc of y. Okay? So that's good. Let's do some examples, maybe. I always start with the stupid example now. So what is, oh, sorry. I can. Is that good? So the stupid example would be, what is the cluster character applied to the zero object of the cluster category? We know that the index of the zero object is 0, and we know that the F polynomial of the zero object is 1. That's 1. Let's do a slightly less stupid example. Let's return to the Kronecker quiver. Let's compute the cluster character of this object here. Yes? So now, what I've drawn on the board was the category of modules for the Kronecker quiver, but now we need to live in the cluster category, and I need to choose a cluster tilting object. So remember that in the cluster category, I have the module category plus n shifted projectives. So in this case, the cluster category will look like this, with 2 additional objects, and they are the suspensions of the projective modules, and they happen to be on the left. of this, of the two projective modules. And then, of course, this continues, but whatever happens here is precisely what happens here. Yes. The cluster category closes up. Now this, the direct sum of these two objects is what I'll take to be T. And the reason I do this is then when I apply my functor f, so hom T suspension blank, yes, to these objects I get precisely the module that is drawn in its place, yes. So I can identify the objects in the cluster category with the module that is drawn here by making this choice. Leave this here. So now I want to compute, for the Kronecker quiver, I want to compute the cluster character associated to this, the cluster character applied to this object of the cluster category. So this is the object such that f of x is this module. T is the sum of the two shifted projectives. Yes. Otherwise, I could add as many copies of T as I wanted, and I would get the same module. But if I specify that X is indecomposable, there's only one, and it's the one appearing here in the cluster category. We've already computed the F polynomial of this module. So let me recall, it's still on the board. It's 1 plus y1. And in order to compute the cluster character, I need to compute the index of this object. What is the index of x with respect to t? Yes, so maybe I should say that the endomorphism algebra of T is isomorphic to the path algebra of the Kronecker quiver. So I really end up in the module category of the Kronecker quiver. And the choice that I've made ensures that if this is the object X in the cluster category, then when I apply F, I get this module of dimension vector 1, 0. Now, there are several ways to compute the index. In this case, we're so close to T that we could just give a triangle containing two terms and add T. But instead, I would like to illustrate one of my remarks from this morning in order to compute the index of X. One of the remarks was that to compute the index of X, it suffices to compute a minimal projective presentation of f of sigma minus 1 of x. That was one of my remarks of this morning. And what is sigma minus 1 of x? Well, in the cluster category, the shift becomes equal to the Auslander-Rayton translation. And the Ausländer rate in translation is going once to the left. So the inverse of the shift, so if this is x, then this is going to be sigma minus 1 of x here. So what I need to do is compute a minimal projective presentation of this module. So in this case, f of sigma minus 1 of x is the module of dimension vector 3, 2. The indecomposable module of dimension vector 3, 2. And a minimal projective presentation has the form, so put the module, and in the first term, so the projective cover are 2 copies of P2. And in the kernel is 1 copy of P1. So this is a computation that that you should do as an exercise. I have mentioned that this is the case in my first lecture. And once you have this, you can lift this into the cluster category and compute the index of x. It will be 2 copies of T2 minus 1 copy of T1. So this is minus T1 plus 2 times T2. Or if you want to write this as a vector, this is the vector minus 1, 2. So the index we've computed now. So we can write down what the cluster character applied to x is. It's x to the power of the index, so x1 minus 1 times x2 to the square, times 1 plus y1 hat. This is the F polynomial applied to y hat. What is y1 hat? And what is y2 hat? You have to look at all arrows going into 1 and all arrows coming out of 1. There's 2 arrows coming out of 1 going to x2. So you get something like this. And similarly, y2 hat is something like this. This is just an application of the definition of y hat. So when I replace this here, I get x2 to the power minus 2. And if I write this as a fraction of polynomials, I get 1 plus x2 squared over x1. So let me maybe write it down here. 1 plus x2 squared over x1. Now, of course, I've got 2 additional objects here, yes, T1 and T2. I should compute what is CC of T1, for instance, and what is CC of T2. CC of T1, that's x to the index of T1 times the F polynomial of f of T1 applied in y hat. But f of T1, this is 0. So the F polynomial is 1. And what is the index of T1? That's 1, 0. We've computed this already this morning. So here I get x1. If you do the same thing for T2, you will get X2. And this is general, yes? If you compute the cluster character of Ti, for Ti, any indecomposable summand of your cluster tilting object T, then you will get the initial variable Xi. So in my picture here, associated to these two shifted projectives, I get X1 and X2. And now maybe the important remark is that this is the mutation at 1 of the initial cluster for the Kronecker quiver. Yes. Remark. If you mutate the seed the initial seed for the Kronecker quiver and you mutate it at 1, you get a seed where, of course, X2 is unchanged, and the other cluster variable is 1 plus X2 over X1. So the cluster character of this object gives me the cluster variable. Of course, then you can repeat this exercise for some of the other modules here. I would say that it's a good exercise to compute what the cluster character of this object is. We've computed the F-polynomial already, so all you need to do is to find the index of the next module here, a module, an indecomposable of dimension vector 4, 3. So to find the index of this guy, you need to compute a minimal projective presentation of this module. And once you've done this, you can deduce the cluster character. Let me give it to you, but you can find it, if you are quick with a computer, you could find it by mutating this seed at 2. It turns out that this is also a cluster variable. Yes, if you mutate this seed at 2, either by hand or maybe this would be a good opportunity to try out Bernhard's applet in Java, then you can find that the mutation here will give you exactly this polynomial. Laurent polynomial. Okay. So you can guess what the idea is now, right? I'm going to say that if you apply the cluster character to any of these objects here, you get cluster variables. And I'm going to say that in this way you get all cluster variables, yes? You have to go back as well, yes? When I say here is stable under connected components of the AR quiver of CQ. So you should go back as well, yes? If you mutate this initial seed, well, this initial seed at 1, then you advance here. But if you mutate at 2, you should go back. And going back here means ending up here. Yes. So remember that even though the module category has a beginning and an end in some sense, the cluster category has one additional slice that glues the beginning and the end together. And so the theorem is the following. The cluster character induces bijections from the set of indecomposable rigid objects in CQ up to isomorphism to the set of cluster variables of the cluster algebra with initial quiver Qt. And CC also induces a bijection if instead of taking indecomposable objects, you were looking at cluster tilting objects. Well, basic cluster tilting objects in CQ up to isomorphism, then if you apply CC, you get a bijection with clusters in the same cluster algebra. Now I've left a blank here, which I will fill up a bit later, in a few minutes. Strictly speaking, in this setting, what is written on the board is correct. Yes. But I would like to add words here so that this statement remains true if you go in generalized cluster categories. So now, I want to say a word on how this theorem is proved. And what I want to explain in the last 15 minutes is the notion of mutation of cluster tilting objects. Not that I will be proving many of the statements that I will write down now, but at least I want to show you how this can be defined. So again, what is my setting? Let Q be an acyclic quiver. CQ is the cluster category, and T any basic cluster tilting object in CQ. I want to mutate T. So recall that my notation for the indecomposable summands of T are T1 up to Tn. So if I have any reasonable notion of mutation, if I want this to imitate mutation in cluster algebras, what I would do is take this object T1 plus T2 plus T3 up to Tn, remove Ti, and replace it with another indecomposable object such that the direct sum remains cluster tilting. Yes? So I will not prove that you can do it, I will just show how you do it. Okay. So what you do is you start with Ti. One is I. And you approximate it by all other summands of T, indecomposable summands of T. So I'll write it in this way, and I'll say that this is an add. Ti hat approximation of Ti And Ti hat is just T, well, this direct sum where I don't take the direct sum in Ti. So I go up to Ti minus 1 and then I skip Ti. And what does approximation mean? It means that if I have any other map morphism like this, where this R is an add Di hat, then this map factors through E. Yes? E is an object in add Ti hat, and this morphism here, together with the object E, are such that this condition is satisfied. So Ti hat here is the direct sum of all Ti's except, well, the direct sum of all Tj's except for Ti. So it's as if I was taking T and I remove Ti from this direct sum. So I have a smaller object, and I say that I look at an approximation like this. So one fact is that such approximation exists. And one of them is minimal. And minimal here could be defined in several ways, but in this context, I will just say that it means that E has as little indecomposable direct sums as possible. So for example, in the Kronecker quiver, and in its cluster category, where I take T to be this object here, so this is T1 plus T2. If I want to approximate T1 by T1 hat, that's just T2, I need to look at all possible morphisms from T1 to T2. In this case, I have two. Well, the space of morphisms from T1 to T2 is two-dimensional, and the basis is given by these two irreducible maps. So if I call this alpha and this beta, then I have two morphisms from T1 to T2. And this is a minimal approximation. Now, once you have it, I'm going to define Ti star to be the cone of this minimal approximation. So recall that in a triangulated category, if I hand you any morphism, you can complete this into a triangle. No, I should not erase this. Okay. Now some facts. If I replace Ti by Ti star in the object T, I get a new cluster tilting object. Okay. And now the theorem that I want to state is that if you mutate a cluster tilting object and then apply the cluster character, it's going to be the same as applying the cluster character, looking at your cluster variable and mutating it. Yes. So how am I going to state this? I'm going to say that let T be a cluster tilting object. Sorry, I'm writing small again. I'll write bigger. Be a cluster tilting object. I choose an index I. Oh, I've written facts here because I wanted to state 2 and I've only stated 1. Here I took a left approximation and I took its cone. I could do the same on the other direction. Yes, I could take a right approximation and take sigma minus 1 of the cone or the cylinder. And the fact is that you get the same answer in both ways. Yes. So if taking right approximations yields the same object Ti star, so now I will consider these two approximations, the left approximation and the right approximation. So I have Ti goes to E, this is a left Ti hat approximation, well, a minimal left Ti hat approximation, and I take the cone. Or I could do it the other way around. I could take a minimal right Ti hat approximation of Ti, and I could complete this into a triangle. And here I get the same object. This is not obvious. This is not true in any category, right? If I take these two, and I want to compare the cluster character applied to Ti star and to Ti, then the cluster character applied to Ti times the cluster character applied to Ti star. So the product of the two extremes is the sum of the two middle terms. Maybe that's all I want to say. And why do I write this? This becomes an exchange relation in the cluster variable in the cluster algebra. Because you can prove that this is going to be the direct sum of all tj's to the power the number of arrows from I to j in Qt. And this here is going to be the direct sum of all tj's to the power the number of arrows from j to I in Qt. You don't get the second from the first. These are two separate computations. So for the first one, you approximate ti by ti's hat in this direction. And for the second one, you approximate ti by ti hat in the opposite direction. And you complete these two morphisms into triangles. So if you look at what happens, you see that cc of ti times cc of ti star becomes, if you apply everything we know here, it's going to be the product of cc of tj to the power the number of arrows from I to j in Qt plus the power of the product of all cc of tj's to the number of arrows from j to I in Qt. And if you were to write this as ui and this as ui star and cc of tj as uj, what you see is precisely an exchange relation in the cluster algebra. And so we get all cluster variables in this way using this kind of mutation. I wanted to add the word reachable somewhere where I've erased, so I'm not going to add it because I've erased it. Tomorrow, in the last lecture, now we know how to get all cluster variables, and hence all cluster monomials, because we know that products in the cluster algebra, this corresponds to direct sums in the cluster category. In the next lecture, in the last lecture, we're going to look at bases for cluster algebras. And these are, in finite cases, in Dynkin cases, bases for cluster algebras viewed as free abelian groups. These are given by cluster monomials. But if the cluster algebra is not of Dynkin type, you need more elements. And what we're going to see is how you can obtain some of these elements from the cluster category. Thank you very much.